So parametric equations are, I think, one of the easier topics in all of calculus. A lot of times they're pretty logical, and the idea behind a parametric equation is you are defining both x and y in terms of some third variable, usually called a parameter. A lot of times it's t. So what you could think of this as being is x is defined by some time. So as you move left and right with time, the kind of fun thing about this is you can have all sorts of weird shapes going on. You can have x be moving to the left while y is moving up. You can have x be moving to the right while y is moving down. All sorts of stuff can happen. So let's see what we got. All right, the definition of a plane curve. If you've got two different functions in terms of t, we've got basically our parametric equation. One of the things that you have to be careful about when you draw a parametric equation is a parametric equation has an orientation. So this fancy word orientation is kind of a big one here. It talks about which direction the curve is moving. So if you think of a curve in parametric as being maybe a parabolic motion problem, maybe you hit a pop fly into the infield. When you draw that parametric equation, it has a definite direction, which is different than functions. Functions don't have time, but parametric equations generally have an orientation. That orientation is not always left to right, sometimes it's right to left. So when you create a parametric equation, you want to try to preserve the orientation by putting these little arrows on there. Alright, so one of the most basic things you can do with the parametric equation is really, if you want to just graph this between t equals -2 and 3, you're just going to plug in points. So we have an x equation, we have a y equation. They're in terms of some other variable t, which is our parameter. It doesn't have to be t, it just has to be another variable. So all we really do is we try plotting points. So -2, if we plug that in for t, -2 squared is 4 minus 4, we get a 0. If we plug it in for y, -2 over 2 would be -1. I would probably suggest doing all the x's just kind of as you go across here. -1 squared is 1 minus 4, -3. 0 minus 4 is -4. 1 minus 4 is -3. 2 squared is 4 minus 4, which is 0. 3 squared is 9 minus 4 is 5. So that's all the x's. Now here's all the y's. So we plug in our -1 to the y, and we get -1/2. Plug in 0, we get 0. Plug in 1, we get +1/2. Plug in 2, we get 1. Plug in 3, and we get 3/2. So now what we're going to do is plot ordered pairs. So we got 0, -1, our first dot. -3, -1/2, so -1, 2, 3, down 1/2. -4, 0. -3, +1/2, right here. 0, 1. And then if we go over to 5, 1, 2, 3, 4, 5, we go up 1.5. So the parametric equation you draw, let's try actually get this. Do your best by connecting dots just like a polynomial, and we can kind of tell that this would keep going, but we don't know what it ends up doing afterwards. So one of the things we want to make sure is that we are putting our arrows in there. We really don't want to go past this point. I know if I erase that little part there, it'll erase the whole line. So do your best connecting the dots and try to preserve the orientation, because t is going from -2 to 3. We start from where we start at -2 and go to 3. Now, a lot of parametric equations are not going to be functions. Like this does not pass the vertical line test at all, and that's not a problem. How in the world are we supposed to eliminate this parameter here for cosine and sine? We really want to kind of smash these together. Now, we can tell based on the way this problem is set up that we've got something squared plus something squared equals 1. Alright, well, here's what we're going to use. We know that cosine squared plus sine squared equals 1. Alright, well, let's subtract over let's solve for cosine. So we get cosine of theta equals, well, x minus h over a. And we know that sine of theta, if we were to subtract k over, would be y minus k over b. And then we also know that sine squared plus cosine squared theta equals 1. Okay, so let's take our sine squared, and we got y minus k squared over b squared plus cosine squared theta, so, oops, sorry, x minus h over a squared equals 1. Oh, look at that. We got that ellipse that we're kind of talking about right here. It's a little bit backwards from what I would have expected to write, because I would usually think of sine squared plus cosine squared, and they kind of got their cosine squared plus sine squared. So what we did here was we eliminated the parameter. We managed to rewrite this in terms of x and y. A lot of times what you do is you solve for a variable. So what we could have tried to do is solve for theta, and we would have needed an arc cosine, and then we'd have to plug back in here. We'd probably get something that would be different looking, but it would be basically the same. So let's talk about what we can do on our calculator. If I had a parametric equation like x equals 2 cosine t plus 2 cosine 4t, and then y equals sine t plus sine of 4t. So they got the graphs here for us, and then the second one's pretty cool. It's called a LaSalle curve. That's kind of a tricky thing to graph by hand. We'd have to try to eliminate the parameter, and I mean, the kind of obvious thing here, we can't use that sine squared plus cosine squared equals 1 deal, because I've got something just a little too complicated. It's going to be hard to solve for t in either of these equations to plug into the other one. I could plot points, but if I wanted to get something complicated like what we have down here, it's really hard to do. So what we're going to do is we're going to go into our mode, and we're going to change this from function to parametric. Let's go down to parametric. Enter, and then when we go into our y equals, they've got x1, they've got y1. So all we're going to do is write our equation: 2 cosine t plus 2 cosine of 4t, and then for our y we got sine of t, what's that up, plus sine of 4t. Nope. I'm missing a sine. Close that up. And now the other thing we want to do is we want to get a good window. And one of the hardest things about this is to look at the window. Now you can see what's graphing on mine, but looking at the picture here, you're noticing that this is really only going to go up to 1, 2, 3, 4. Okay, so I'm going to go from 4 to negative 4. Let's make my window that do that. Now you notice that the window has T-min and T-max. Now that really depends on the problem. Oh. Depends on what you're looking at. So we're going from 0 to 5. So my T-min would be 0. My T-max would be 5. What you saw there was 2 pi. Okay, so T-step. So this says how far apart do you want each of these things to be. The smaller you get, the more accurate your graph ends up being. If you do 0.01, it's only going to plot a point every 0.01. And then our x-min, let's go negative 4. X-max will be 4. So this second part here is pretty much the exact same thing. Y-min, x scale, we'll just go by ones. Let's forget the scale. We'll go from negative 4 to 4. And now let's look at the graph and see if we get something that looks a little bit nicer. Now it's taking a long time to plot because I went by every 0.01. Now you can watch what happens if we go and change it to like 1. It really will only plot every 1, and it'll go really fast, but at the same time it'll be kind of jagged. So it's plotting points and connecting the dots, what it's doing. So the more precise you make the t-step be, the longer it's going to take to plot, but the better your picture is going to be. Now, what do you think would happen if I didn't stop this at 5? So let's do a couple things here. We're going to go back and we're going to change this to 0.1 so that it goes a little faster. You can change it to 1 if you want to. And we're not going to stop this at 5. We're going to stop it at, let's double it up. We'll go to 10. Watch what happens. Now, first off, we can tell it's tracing a whole lot faster. Oh, it kept going. But then what you notice a lot of times, not always, they double back on themselves. So it finished out the curve, but then it went right back into it. A lot of times they're periodic in nature. All right, let's talk about limiting a parameter before we move on here. So we got two sets of problems here. We got x, which is in terms of t, and y, which is in terms of t. So what we want to do is really just take one of these equations and solve it for t. Generally, you solve t for x. So t would be x plus 1 over 4. And then all we're going to do is use substitution. So we end up with y equals 2 times x plus 1 over 4 plus 3. Or y equals 2 over 4. So the 2 and the 4 cancel out, leaving us with a 2 on the bottom. X over 2 plus 3.5, so that would be 7/2. And what we can always do is we can plot the original one and the rectangular one on the same graph. Actually, you'd have to go into function to plot the rectangular one, but that's really it. So all we got was a line out of this. All right, let's try out b as well. So your t would be x minus 3, and then so your y would be x minus 3 squared. So what we're going to do for d here, which looks a little bit tricky, is we're going to solve for t. And one of the ways we can do this for this particular problem is we could try to complete the square. So we take half of our middle term and we square it. So t over 2 squared would be, well, half of our, just the number. 1 over 2 squared would be 1/4. We got to add that to both sides. So the left would be x plus 1/4. And the right ends up as factoring as t minus 1/2 squared. So all we're doing is completing the square for both sides, and then we square root both sides. So square root of x plus 1/4, that would equal our t. So we end up plugging that right back in. So we get the square root of x plus 1/4 squared, so x plus 1/4 plus t, which it would be the square root of x plus 1/4. Now, one of the weird things about this is there probably should be a plus or minus here, right? To get square root, we have a plus or minus. When we square it, doesn't really make a difference, but over here, we should probably have a plus or minus. So let's see how that looks. What in the world is that plus or minus about? So we're going to plot our original in the calculator, see what happens. Then we'll plot our second one as well. And let's actually make our window go from, let's go to positive 10. Let's go from negative 10 to positive 10. And there we go. So we have the positive half, and we've got the negative half. So without that plus or minus the square root, you won't get that when you actually try to plot it in the function. So we go to mode. If we change this to function, and then in y1 we get, what was it, x plus 1/4, I believe. And then we have plus the square root of x plus 1/4. Oh, I don't need that one because we got the new operating system. And we can kind of tell right here that it's the same thing on the graph that we saw a minute ago. And if we put the minus, we should get the bottom half of it. Waiting for the graph to kind of jump around for me. So there was the first half, and here's the second half. Put them together, you get the plus or minus, and you've got the equations that we were kind of expecting. You just double check, make sure that equation is right. Yep, looks good. So we can check these with parametric. These parametric with the actual. That was not even close to what it was. With the actual functions, we gotta change our mode around when we want to go between the two of them. So there we go.